Hi, welcome. Thanks for showing up today on this nice Tuesday rainy afternoon. Announcements. Register your final project teams until Thursday. There's a survey on Piazza. So on Piazza, there's a note that should be pinned where you can find a link to a Google survey there, and that is just going to ask you for the names of your team members and the tentative project title. And that project title can be changed afterwards. I just want you to have a discussion within your team members to see that you have common interests, right? So, and please register your teams until Thursday. And I just got a question what we're looking for in the final projects. And my answer to that is show off. Right? Show us what you all learned in this class and make us proud that you are great data scientists now, right? Like go over, scrape something from the net and then do exploratory data analysis. Have a look at that data set and tell us the story of what you all can find and interesting things there, trends that nobody thought would be in there, and then even do some machine learning problems. I actually have a question for that, and that is what would you like to see most in class? I realized so far my outline is basically classification. We're going to do decision trees leading to random forests, hopefully today. And then I have support vector machines coming up because I believe those are the two most popular classifiers out there that people normally use in supervised settings. We're going to have at the very end one lecture on deep learning, just because it's all the hype at the moment, right? Google with their big neural networks. But I don't really expect anybody to use that in the final projects, just because it's hard. And there's a big learning curve there. Like there's a reason that random forests and support vector machines are very popular because they're easier to use and to implement. And they're also faster and they're more suitable for the size of data sets you most probably are gonna have. But I have also materials, and we're going to see some stuff about unsupervised learning. And I don't have much about regression at this point, because Raphael showed a bit of regression. You have seen or will see a bit of regression in the homeworks. So I have the question, so regression, just to make clear, when I say regression, I mean supervised setting where your prediction is not just a category, right? It's not oranges, apples. I give you the size of an apartment and you give me the price. It's a continuous variable you're trying to predict. Who knows already that they're going to face a regression problem in their final project? There's a strong interest in that. One group. Okay, that is not the vast majority. We're going to go over a bit over regression anyway, so you guys are going to have something to do. If that is not enough for you, please just shoot me an email. We can talk, right? So I can give you a bit more techniques for your project, like if the general interest is not overwhelming. Then I'm going to stick mostly to classification problems. Yeah, and then once you filled out this survey and registered all your teams and got everything together there, the next thing that is going to be due there is the actual project proposal. And that is going to be due on the 17th of November, just to give you the heads up. And I think what we're going to do is another Google survey that is going to ask you about more details about your project, right? An abstract, the methods you're planning to use, and very, very important, how you're going to obtain the data, or if you already have the data, what it looks like, right? For a data science project, it's very important. Like this should be on your mind now. What data do you want, and how do you get your fingers on it? Okay, I've just been asked where you can find more background information about the machine learning stuff I tell you about. These are the two books that I use the most to steal figures from. They're both heavy on math, not too heavy, I believe that you can understand that, but it's going to take a bit of time. I'm actually leaving out a lot of math here and trying to convey the intuition behind the machine learning algorithms. If you really go into the books, there's going to be a lot more formulas there. But if you go over that first step, right, and go into it, most of it just boils down to here's a loss function, and this is how we minimize it. So this is the elements of statistical learning. Is actually, I think, downloadable on the web. This is from Stanford, from a statistics group. And it's very good if you want to learn more about decision trees and boosting and random forest, what we're going to do today. And the Bishop is also very nice with intuitions. And I'm not sure if it has what the different focus is. It's also sometimes nice to compare them. I think the only recommendation I have is for the first book, like if you want to learn more about especially gradient boosting, that's very well explained here. And otherwise also consult the other book, because sometimes it explains maybe things in a more intuitive way for you to understand stuff. So as I said, upcoming today, classification and regression trees. This is a very simple classifier that is nice and fast, but not performing so well. So people try to fix that problem, and that is where we come into ensemble methods. We're going to go over bagging and random forests. And if we have more time, we're going to talk about boosting and cascade classifiers. So, but first, the decision trees. It's really just what you see there. So a tree is an acyclic graph, right? So you have your root node. And then think about these flow diagrams where you try to make decisions. So what should I do tonight? Is it after 10 p.m.? If no, you can call a friend. If yes, that friend might be sleeping. So the question is the electricity working? Did you pay your bill? If no, maybe you want to read a book in candlelight. If yes, did you get a new DVD? If no, you can still play a computer game. If yes, you can watch TV, right? So this is a very simple example of a decision tree. You have this tree, and at each node, you're queried one question. You answer yes or no, and depending on your answer, you go to the next node. That's the whole concept. So decision trees are nice because they're very fast to train and fast in prediction, right? Like, ideally, if you do a search also, you want to search something in a long list of words, and it's in alphabetical order, you can split it in half, right? And then you know whether the word is maybe in the first half or in the second half, and you go down. So this can be very fast, and they're easy to understand and easy to interpret. This is very nice, because if you train a tree automatically, you're still going to end up with these type of rules. And a lot of people like that, especially in medical contexts. Right? If you train one of these deep learning neural networks, you get state-of-the-art results, mind-blowing away, but nobody knows what's really happening inside that network. It's a black box, right? You put data in, and you hopefully get a good prediction out. And a decision tree is called a white box, because you can open it up, you can look at all the rules, right? And you can see what it learned and see how it's trying to do what it does.